I'm happy to have Arsen here. Arsen is a Simon's postdoc right now for this semester, and then you're coming to IFML next semester, right? Still? Okay, that's the plan. He's going to be an IFML postdoc next semester. I heard that you had a headache yesterday.
Yeah, I feel better now.
Okay, yeah, no, I was jokingly telling Kostas that it's because your brain must have overheated. Arsen is very smart. So, but he's been working a lot on testable learning, and yeah, take it away.
Thank you. So I'll tell you today about our upcoming work on testing noise assumptions of learning algorithms. And this is joint work with Serbi Goel, who's also around, Adam, and Kostas Stavropoulos, who is sitting here right now. So feel free to chat to any of us about this work. Let's start with some background about learning with noise, with label noise. So what's the setup? So your learning algorithm is getting a labeled dataset S, and it wants to give you want a good classifier for the dataset. And so learning with label noise is the setting where you have some function class, let's say the class of linear classifiers, and the labels you get for your dataset are not necessarily perfectly agreeing with one of the functions in your function class. So for example, maybe there's a half space that does pretty well, but maybe no half space does perfectly on your data distribution. And learning with noise, you still want to do something. You want to find a classifier that does almost as well as the best classifier in your function class. So formally, if error f is the probability of misclassification, so the probability that you get a new fresh sample was the probability your predictor f misclassifies. You want to find a predictor that's approximately optimal, that has an error, optimal error plus epsilon, where opt is the best misclassification error in the function class. Yeah, so here there's some linear classifier, some half space that does the best, and our goal is to approximately match that. So this is the overall setup we'll be talking about today. And I'd like to emphasize that statistically, this type of question is very well understood. So if you're not constrained in terms of runtime, you can use the following fact, that if you have enough samples, then for every classifier in your class, with high probability, the prediction error of this classifier will be very well approximated by the error on your training data set. Okay, and we know for all kinds of classes exactly how many samples you need in order for this type of thing to hold. So for example, for linear classifiers, something like a polynomial in d over epsilon is more than enough for this type of thing for this discrepancy between these two values to be small. And then of course what you can do is you can just fit the best linear. If you are unconstrained in terms of runtime, you can just look at all the classifiers in your function class, fit the best one, and that will satisfy this approximate optimality condition. So in terms of statistics, in terms of how many samples we need, these questions are very well understood. But on the other hand, if you are constrained in terms of runtime, all these questions become much more complicated. So in particular, it's known even for the class of linear classifiers, so sort of one of the most basic and well-studied classes in learning theory. The following task is NP-hard. So the task of someone gives you a data set, if it's a fully worst-case adversarial data set, what's the try to approximately find the best linear classifier for this labeled data set. So that task is NP-hard, probably requires a time that's something like 2 to the d dimension. And even if you are allowed to assume that your data points are coming from the IID Gaussian distribution, but your labels are worst case, so your labels for your data set are fully adversarial, then still, based on certain cryptographic assumptions, this problem is believed we're pretty sure this problem cannot be done in polynomial time. So how can you get around it? So even assuming structure on your data points, so it gives you hard instances. And because of that, a lot of literature has been studying the problem while making assumptions on your example, on what the labeling function is. So assuming structure on the labeling function. So and in particular, sort of the state of the art, so one of them, the most general type of family of noise models that people have studied is called Massart noise. Let me actually, Ankur gave a talk, I think a month ago. Part of it was about Massart noise, and I recommend you all to check it out. And let me define for you what the model is. So there's some ground truth half space. So there is some linear classifier that's the ground truth. And for each example, with some probability, an adversary gets an option. With probability eta, an adversary gets an option to flip the value. So the ground truth value is the sign, v ground truth dot xi. So with some probability, the adversary gets to corrupt it and give you the opposite label. And otherwise, it's not corrupted. So either if the adversary did not get the option to corrupt it, or if the adversary got the option to corrupt it but did not choose to do it, then you get the correct label. And a long line of work that's started by Vashti, Balkan, Hakdalab, and Euler, and sort of the last paper in this series is Diakonikolas, Kondonis, Tsamos, and Zarifis, show that you can, if your data points are standard Gaussian and your noise, your labels satisfy this Massart noise model, you can get the error O plus epsilon in time, in fully polynomial time. And I just want to say a couple words about why people have, like, what's the kind of motivation for studying Massart noise. So it generalizes this other model called RCN, random classification noise model. And what that model says assumes it's that with some probability eta, let's say 0.4 or something, every label is flipped. So there's some ground truth half space, and the label is flipped with some probability that's the same for every single sample. And but then when people started studying this RCN model, so the model of like uniform flips with equal probability in the whole space, turns out you can take advantage of the structure of the noise. So for example, what you can do is you can sum up all the positive points and subtract all the negative points from there. And what ends up happening is, like, if this is your ground truth half space, if you compute this estimator, then so you'll get signal in the direction of the right ground truth half space, and all the noise in all directions will cancel each other out, because in all the space the probability of flipping is the same, so the noise will have this nice symmetry property that it will cancel itself out in all directions. And Massart noise allows you to model more realistic scenarios where, for example, you can assume you can model situations where there is some region where the noise is, let's say, 0.4 here, and some other region where it's 0.3, and some other region where it's 0.2, which is much more realistic and doesn't have this nice property of cancellation that you can take advantage of. And also this algorithms that do learn under Massart noise look a lot more like the ones people use in real world. They used SGD on logistic loss. You have a question?
Yeah, so you say you can get error of plus epsilon. How
Yeah.
do you define opt?
Oh yeah, opt is the best error among all half spaces. Yeah, it's a Any other questions? Okay, thanks. Yeah, thanks for asking. So, okay, so let's do a summary. So, you go goal is essentially you're given a data set, you want to fit the best half space to the data set. And if you assume certain things about the noise of how what model your labels satisfy, you can achieve this task of getting an error of plus epsilon. But what if you really care about having optimal error? Yeah, so what if you're really worried about the error not being optimal? Then can you say okay, it has to be optimal because this theorem in this we're using this algorithm and we have this theorem, it says it's all plus epsilon.
Is that your brain on the left?
Yeah.
Oh.
Yeah. It's tormenting me at night. But what if the noise is not Massart? And since one of the premises in the theorem is that the noise satisfies this Massart property, if the model did not really hold, what can happen is that the premise of the theorem is not true, so you cannot use the conclusion. So it could very well be that this algorithm they used got stuck in some local optimum, and what you have is like grossly suboptimal compared to what the truly best half space is. So that motivated us to introduce this new framework of testing noise models. So your algorithm now has two options. So it's again given a labeled data set. It can either say accept and give you a classifier f, or it can say I think the assumption is wrong, reject. And it should satisfy the following two properties. So first, soundness says that if no matter what labeled data set you're given, if your algorithm accepts, then it has to be the case that the classification error of your classifier f that you got should be at most the best error among all half spaces on this data set S plus epsilon. Yeah, so if you are in this case, if it says accept, then what you get has to be approximately optimal, on this data set you're given. And on the other hand, completeness says essentially that it should do everything that. So if the assumptions do hold, if the samples data points are Gaussians, and the noise satisfies this Massart assumption, then it should, with high probability, say accept. Yeah, so it should do the same thing as those algorithms that learn under Massart noise do. So those are the two conditions. And I'd like to emphasize this. It's assumed the noise rate is at most 0.49, and that's what all those other papers are assuming too. And you can assume anything up to 0.5. And that at 0.5 there is a phase transition and the problem becomes computationally hard, even if you don't need to test, even if you just want to get O plus epsilon. And so our main result is that you can achieve this. You can achieve this more stringent requirement of a testable learning algorithm. And that runs in time poly d over epsilon. And the way I like to think about this is that you get a labeled data set, your algorithm gets a labeled data set, and two things can happen. Either you get a classifier and you get a certificate that this classifier, this half space you got is epsilon optimal compared to all half spaces on this data set S that you got. Or you get a warning, or your algorithm says reject, the assumption doesn't hold, so it detects that your noise did not satisfy this Massart assumption. And to conclude, so now if you use this algorithm, and you're very worried that what you got is not approximately optimal, you can tell yourself that the algorithm said accept, and therefore, no matter, even if the assumption didn't hold, the fact that the algorithm said accept tells me that what I got is epsilon optimal. And I'd like to just quickly say a couple words comparing this to this previous work in testable learning. And so previously, so what was being tested in testable learning is the marginal, that the data points come from the Gaussian distribution. And they were in this agnostic model where there was no assumption on the labeling. So here we do So our work tests the, so you get this O plus epsilon error guarantee and poly d over epsilon runtime, which you could not achieve in the agnostic model. And I'd like to emphasize that testability lets you do what we call algorithm selection. So if you are not sure if your data points satisfy the Massart noise model, you can run this algorithm, and if it says accept, then you're happy. You know what you got as error plus epsilon, and if it says reject, you can go ahead and run one of these other algorithms, and it's sort of a win-win in this situation. So let me talk about the main ideas going into this. And let's first focus on the random classification noise model. So let's focus on the easier problem where your algorithm, our algorithm has to accept only if the noise satisfies the random classification noise, sort of uniform flips throughout the whole space. And again, there's going to be, we show there's a phase transition at 0.5. So at 0.5, the problem becomes computationally hard. So you have to the random flip rate will be at most 0.49, and you can make this any constant less than 0.5. Okay, so here's the kind of the overview, kind of the plan for the algorithm. So you get a bunch of these points. So you get a bunch of data points. Some of them are labeled +1, some of them labeled -1. So first you run this algorithm that I explained to you works for random classification noise, and you approximately recover. So that approximately recovers the ground truth half space. So you try to recover it. So the step, if the assumption is true, will give you something very close to the ground truth. And then what you do is you separate out the points on which this classifier you got gives you the wrong answer. So those going to be the points that have value -1 in this region, and the ones that have the value +1 in this region. Okay, so once you separate the points out, here's the plan. You want to certify the following properties. So you want to certify that for all W prime in the d-dimensional space, so for every other half space, the following holds. So the fraction of the points first in your original dataset S that you got, in every region of this form, where the half space U, kind of your current classifier, and this classifier based on W prime disagree. So there's like this region in space. The fraction of points there is at least something close to 1 times what it should be for Gaussian distribution in expectation, minus epsilon. So that's the first condition. And the second condition is sort of the converse, but for just this element in S incorrect, on which your algorithm is making an error. So this is the plan. So we want to certify these two properties. And why is this useful? So let me argue that if we do that, if we succeed to certify this for all W prime, then we will have a certificate that this half space is approximately optimal. So suppose it's not. Suppose we choose some other half space, W prime, as our new half space. So this first condition, the second condition allows you to conclude that the number of mistakes you fix as you move from W to W prime cannot be too large. So in particular, if you substitute everything in, it will, and we also check this condition. Maybe I did not mention that. So you check, so when you look at how many points you're making an error on, you verify that there aren't too many of them, and if the noise rate is at most 0.49, the fraction of errors you're making should be at most 0.495, for example. And if you substitute all of this in, you can conclude that as you move from W to W prime, the number of mistakes you fix should not be too large. But on the other hand, these two conditions together allow you to conclude that the number of new mistakes you make when you move, if you choose W prime instead of W as your linear classifier, will actually be large enough. And these two conditions directly imply that at this any half space W prime will not choosing that instead of W will not give you more than epsilon gain in total accuracy. Okay, so these two being able to certify these two conditions for all W prime in your d-dimensional space directly allows you to conclude optimality. And now completeness. So what can we say about the sets S is incorrect? So on one hand, we know S if the assumption is true. If the assumption is true, we know S consists of IID Gaussian data points. And what about S incorrect? So we know if the assumptions were true, in the first step, the classifier W we got will very high probability be super close to the ground truth classifier. And if you let's make a simplifying assumption that we exactly recovered the ground truth classifier. Then this set S incorrect, I claim will also consist of IID Gaussian points. So why? Because every point in the random classification noise model, every point has the same probability of being flipped. Right, and because of that, this set as incorrect will also approximately consist of IID Gaussian. So really, you don't exactly recover the ground truth half space. It's like approximately close, but that turns out lets you conclude this distribution is close in dV distance to Gaussian. And for this presentation, we'll just assume you recover it exactly. And so the goal is to certify these two properties. Yeah, so the new goal now is the following. Someone gives me a data set, and so now I kind of collapse these two properties into one. And you want to certify that for every W prime, the fraction of points in the data set that fall in this region where two half spaces disagree is very close to what it is in expectation for the Gaussian distribution. So you either certify this property or you detect that this dataset S is not really coming from a Gaussian. And I want to give you so I think it's valuable to give you to show you how to certify a weaker property. So here it's like super close to like what exactly it should be. Let's replace that by some constant. Let's only certify the upper bound, and I'll also only certify the upper bound. And I think it's valuable for me to show you how to do that. So it's not exactly going to be what we need, but I will say a couple words about that. But here, I think it's valuable to show you because I can show you this without waving my hands at all, how to certify that. And here's how you can do it. So first, you can show without loss of generality, you can assume this angle between W and W prime is a multiple of epsilon. Because if it's not, you can just kind of move W prime away and to the closest multiple of epsilon and use the fact that you showed that this is the case for the multiples of epsilon. So that's without loss of generality. And here's what your certification algorithm will do. So it's going to go over all these multiples of epsilon, and it's going to look at this strip of thickness alpha around so the points whose projection to W is at most alpha in absolute value. And if it's suspiciously many points there, it's going to reject. That's first step. Then it's going to compute this matrix M alpha. That is this average. So it's XX transpose times the indicator that we're not in the strip, divided by, weighted by like 1 over W dot X squared. So the points closer, having smaller projections, are going to have higher weight. And then you check that this matrix is at most, in the spectral sense, is at most what it should be in expectation for the Gaussian distribution. So by design, this is designed in such a way so if everything is Gaussian, this will accept. So I will argue to you that if it accepts, then this property that I mentioned holds, right? So this region for HW prime consists of these two kind of triangles. Let's just bound the top one. The bottom one is bounded exactly the same way. So you can intersect it with the strip. So the number of points in the strip is at most O of alpha, and alpha is the angle between the two. Plus the probability it's in this region that's above the strip. And if we call this chi, we can rewrite this as this. So the probability that this indicator outside of the strip times the ratio is bigger than 1 over tangent of alpha. And then turns out this is exactly like the expectation of the square of the left side of this inequality is exactly how W perpendicular transpose MA, the MA acting on this vector W perpendicular as a quadratic form. And then we can use the Markov's, the Chebyshev's inequality. So it becomes tangent alpha squared, which is up to a constant alpha squared, times this quadratic form. And then we can substitute we can substitute this inequality that we checked, that M alpha is at most what it should be under Gaussian as a quadratic form. And then we can just compute this value for the Gaussian. So, and what you get is this one-dimensional integral that's quite straightforward to check, is at most something like 1 over alpha. So overall what you get is O of alpha overall. So this allows you, so I just showed you the soundness. The fact that if your test passes, then what you indeed get this property, that all of these disagreement regions have something like something at most angle plus minus epsilon. And so for what we need to do, we need to show like kind of a lot of CRISPR bound, right? So here we lose some multiplicative constant. We want to not lose anything. Yeah, we want a lot CRISPR bound. And what turns out you can do for that is you can use this thing called the band tester. So you can break your d-dimensional space into a bunch of these bands of thickness epsilon, and for each of the bands and all the monomials of degree at most k, you check that the average on your data set of monomial times the indicator x is in the band is very close to what it should be under Gaussian. We show that for constant k, this is clear that for constant k the runtime is poly d over epsilon. And what we show is if, so this here again, if the distribution is Gaussian, the tester will pass. And we show that if the tester passes, then we indeed have this crisp bound that I told you about earlier. How much time I have? Like 3 minutes, is that enough?
Yeah, that's fine. Yeah.
Okay. So I'll just tell you a couple words about what extra ideas come for Massart. So far I was telling you about random classification noise. What do you need for Massart? And for Massart, I remind to you this adversary has an option. So with probability eta, the adversary gets an option to flip, but it might not flip. Yeah. So overall, RCN, the random classification noise model, corresponds to the situation where the adversary always chooses the option to flip whenever the adversary gets the option. But in Massart, sometimes it might and sometimes it might not. So you follow the same type of approach. And so what breaks? So you separate this as incorrect, you check there are not too many of them, and you check these two properties that are essentially the same that I showed you earlier. So the soundness part is the same. So here is what changes. So this property star, we verify the same way I showed to you. But this set as incorrect, now you can no longer allow to assume it consists of a bunch of Gaussian points. Because every time adversary for a bunch of points might not choose to corrupt them. Yeah. So if the adversary always made the option to corrupt, the set as incorrect would be Gaussian. But now, since sometimes the adversary has an option not to corrupt, your data set now consists of a bunch of Gaussians, it's like a subset of a Gaussian set of points. Yeah, so what you need to do now is the following. You want to make a tester that's monotone under data point removal. So if you're, so it needs to certify this property for any data set that's generated by first taking a bunch of Gaussian data points and then removing some adversarial subset of those points. And so turns out the band tester doesn't work for this because you can bias this band tester quite a lot by just removing data points. So just checking that this equals. I want to emphasize the band tester doesn't work, but we show that there is this sort of alternative tester that builds on previous work I had with Serbi, Abhishek, and Kostas that looks at this sort of PSD matrix. That's so x tensor k times x tensor k transpose times the indicator of each of the buckets. So you look at this average and you make sure it's at most what it should be for the Gaussian distribution plus some small error term. And the way I like to think about this is this corresponds to checking that for every polynomial of degree at most k, this average on your S incorrect of b of x squared times the indicator of a bucket is at most what it should be under Gaussian plus some error term. And we show that, so again by design, this will accept the Gaussian data set. This will also satisfy the monotonicity under data point removal, because if you remove data points, you can see this left side of this inequality can only decrease if you remove a bunch of data points. And we show that again, if this test passes, you can have this property that these regions have at most what they very close to what they should under Gaussian distribution. So, yeah, thank you very much.
Question? Yes.
Explain the equation about the dependence on k bounds. So there are few error bounds which depends on k over the volume. How are these derived?
Yeah, it's so it ultimately comes from this question of that was studied earlier, where you have like a threshold function in one dimension, and you want to approximate it by a polynomial. So if you want error, if your polynomial has degree k, what's the approximation error you'll have? And there it turns out it's 1 over square root k roughly, and we kind of use those polynomials and inherit that dependence from there. Thank you. Yes?
Yeah, if my tester fails, like,
Yes.
how do I interpret that? What guarantees do I know?
So either your data points were not Gaussian, or the noise is not Massart.
It's like with high probability, or like.
Yes. Yes. That's inherent. Yeah.
I guess if that happens, then you basically decide to run an agnostic learning algorithm, which is computationally more like what you were saying.
Yeah.
You know, then you go, okay, I have to fall back to these other slower algorithms.
Yes. Yes.
So the way you described certifiability problem for Gaussian is very geometric.
Yes.
So I'm wondering, like, is it sort of limiting to half-space problems, or like could you use similar ideas for other problems where like they perform well if it's Gaussian with some correction?
Yeah, possibly. Maybe for polynomial threshold functions. I heard people have studied those under Gaussian. Yeah, I think this question of what you can learn, like which problems does Massart noise help with, it's an active area of research. So do you have any ideas, Adam?
Oh no, I guess your point is, you know, most of the classes that have been studied, even just plain old Massart noise, forget about checking whether the noise is actually Massart. Yeah. Even there, it's typically limited to like geometric classes. So first you would want to kind of expand the set of concept classes for which we can handle Massart noise. Then maybe you could use these techniques to then test the errors. Any other questions? Okay. Thanks a lot, Arsen.
Thank you.